All right, so sometimes it's the case that we've got a messy function, a polynomial that isn't easy to find the zero of. So if we're trying to find or approximate a zero, which is an x-intercept, so it's important that we remember that from our earlier days. All right, so we need to remember that a zero is an x-intercept. All right, so it's anywhere the graph crosses the x-axis. It's a zero. So if our polynomial is not pretty and we can't just figure it out by reading it off the graph, we do have a technique called Newton's method to approximate the zero. And it's really just an application of our tangent line equation, which I've reproduced for us below. So we're going to play with the tangent line equation, and we're trying to find a zero or an x-intercept. So what's true about when we're looking for a zero? Well, our y coordinate is zero, right? And we're looking for this x-intercept. So our tangent line still applies. And since we're looking for the x-intercept, we've got this x1, which is going to be our best guess. All right, some point close to the intercept. And we've got this point x here that we're going to be trying to solve for. So to do that, we divide both sides by, whoa, I don't know what I'm writing. F prime of x1, right? So then I've got, well, x minus x1 equals negative fx1 over fx1 f prime x1, and then I add the x1 to both sides. All right. So this is the equation we're going to be using. However, the process is iterative, which means that we're going to get from a first guess to a second guess. So we can just keep repeating this process again and again and again. So this equation is would get us from the first guess to the second guess. But if we wanted to write it generally, we would say, well, x to the n is the same as x to the n minus 1. Whoa, that is not an x. X to the n minus 1 minus f of x to the n minus 1 over f prime at x to the n minus 1. So generally speaking, we're going to repeat it until our zeros are fairly close to each other. So the problems will sometimes define how close they have to be. But for now, it's important for us to understand the process. So this equation right here, or the specific form for finding the first guess, is going to be what we're working with today. So let me just grab that guy and bring it down with us. Pause the video and take a moment to write down our steps here. All right. And then we'll look at some examples. So we're given the function x squared minus 2 here, and first guess of x1 is equal to 1. All right, so we're going to go ahead and find, we'll do 2 iterations, because why not? And an iteration just means I'm using the equation once, so I'll get my x2, and then I'll use it again to get my x3. So here, my x1 is 1, and my equation is x squared minus 2. So our first step is going to be to record that equation, right? And we have to find the derivative as well. And then once we have that, we're ready to set up our equation. So we've got x2, we've got x1, minus f of x1 divided by f prime of x1. And it's just a substitution game now. So I've got 1 minus f of 1 divided by f prime of 1. And I substitute in 1 minus f of 1 is going to be 1 squared minus 2. F prime of 1 is going to be 2 times 1. So I've got 1 minus, my numerator here is going to be negative 1. My denominator is 2, so I've got 1 plus a half, or 3 halves, as my second estimate. All right. And then we're going to go from there to get our third estimate using the second estimate. So for our third estimate, the same equation applies. Just now we're using our second value. So we've got 3 halves minus, and now we're substituting in 3 halves. And then we've got 9. Oof. Try and write that a little better. 9 over 4 minus 2. Least common denominator is 4, so multiply by 4 over 4. We've got 9 minus 8 over 4 over 3. Right, 3 is a whole number, so we can multiply by the reciprocal, 1/3. We got 3 halves minus 1/12. Least common denominator again, multiply by 6 over 6. 18 over 12 minus 1 over 12, or 17 over 12. And that's our third guess.